Thanks very much, Lou, and thanks for everyone for coming out so early on a Sunday. That was an interesting presentation, Lou. That's a lot of good information there. My presentation will be focused on some of the practical aspects of things we've done, at least in Tennessee, to solve some of the problems that you run into when you're trying to engineer a bridge for seismic loads. What makes Tennessee unique? Well, one of the things, you see Nashville right there in the center. Down in the lower left, you see Memphis. That's the most heavily populated city in the Mississippi Embayment. And then on the right, you see Oak Ridge. That's the site of the Oak Ridge National Lab and the Y-12 National Security Complex. Now, generally, as you move from, say, Nashville, either way, the seismic hazard gets a little more severe. You get some effects from Charleston and Oak Ridge and, of course, Memphis. So the northwest corner of Tennessee there, north of Memphis, that's where the new Madrid fault system lies. And it's produced those large earthquakes in 1811 and 1812. Historically, site factors for seismic design have been based on what's happening in the top 30 meters or the top 100 feet of the subsurface profile. In Memphis, you've probably got, 600 to 900 meters before you ever get to rock. So for a long time, we've known these generic site factors really are not appropriate for a place like Memphis. That's the Mississippi Embayment outlined in green there. The more intense green is the deeper subsurface profiles. Around the perimeter of that embayment, generic site factors might have been appropriate. But right in the middle of it, it's highly questionable. I'll talk about several case studies, and each of those case studies is located somewhere in that Mississippi Embayment. This first bridge I'll talk about is State Route 385 over the Wolf River. This is in Shelby County. Memphis is in Shelby County. This actual site is actually a little bit east of Memphis. This bridge, this is a Google shot, and it's actually over 3,000 feet long. It started out as a 720-foot long bridge. I actually had it designed at 720 feet. And then the environmentalists got a hold of it, and they decided this is wetland. So it turned into a 3,000-foot long bridge. And they were probably right. It's probably wetland. The flooding happened during construction. So I definitely appreciate what the environmentalists did. We would not have wanted to have built this 720-foot long bridge. This is a good one to talk about at the ACI Concrete Convention. I'll give you some summary statistics here in just a second, but concrete was heavily used on this bridge. So I'll talk about that a bit, but I'll also talk about why is this unique and what did we do that's unique for this bridge for seismic resilience. That's during construction. So there were 8 bridges on this project. The one I showed you before was the main one, the 3,000-foot long bridge. But 8 1/4 miles of pre-stressed girders, 5.5 acres, precast panels, almost 4 miles of precast concrete. Appropriate to talk about it. Now, what's unique about this bridge for seismic is these, I call them pipe restrainers. So you can see we've got these, think about this, you got this 3,000-foot long bridge. It's really built as 4 separate units for thermal expansion and contraction and things like that. Not only do we need to accommodate thermal expansion and contraction, we need to accommodate seismic movement as well. So the idea behind this pipe restrainer is that it will permit these double vents back to back. Permit them to move longitudinally. It'll resist transverse movement, which could destroy the expansion. So that's the unique thing about this one. There's 4 of those double vents. And you'll notice also that we use pipe piles on this. Now, you can see those pipe restrainers, those little purples, those pipe restrainers installed. So those prevent those back-to-back vents from moving transverse. We use pipe piles on this. new term for that is concrete filled steel tubes. And there's a lot of progress that's been made by Mervyn and others in how to design those concrete filled tubes. The new performance-based design guidelines give some strain limits for those. So those are very useful. Pipe piles, CFST, they're used a lot in this area. It's a really good way to build a bridge in that deep embayment, especially when you've got tricky foundation conditions. I'll also talk about, this one's also in the Mississippi Embayment. It's kind of on the perimeter of that embayment. This is actually in Jackson, Tennessee. This is an interstate bridge over State Route 5. And this bridge is really wide. It's an interstate bridge, 129 feet wide. I'll talk about the span length in a minute, but this thing is so wide, this thing is acting almost like a rigid block in either direction. 15 girder lines for aesthetic reasons. We got these oversized columns. So the prospect of designing those foundations for the plastic shear of these oversized columns, you really pay for it in piling if you don't do something to mitigate that. Because you do. You've got to design those footings for the plastic shear of those columns. Unless you do something like seismic isolation, which I used on this project. The spans are 95-foot end spans with 156-foot center span. And remember I mentioned this thing is 129 feet wide, so it's really like a rigid block. I looked at non-isolated periods on this bridge. This is really stiff. Direction, you got a natural period of 0.21 seconds, 0.76 longitudinal. We add all that together, so it's really wide, so it's going to act like a rigid block. It's got these oversized columns and really short natural periods. Really a good candidate for isolation or partial isolation. By partial isolation, I mean we put isolators at some of the substructures, usually maybe the pier, or in this case the single pier, and then leave the above it. Lee mentioned that historically we've designed for the 1,000 year, the ground shaking with the 1,000 year. For these isolators, I designed those for the 2,500 year. For something like this, you do need some margin. We've recognized we need that margin for a long time. So the performance-based guide and the new guide specs, we have, and the new risk targeted ground motion, we have means of accommodating that without having to resort to engineering judgment strictly. So I did a preliminary design of these isolators, and I used the substitute structure method. It's been around a long time. Dr. Kowalski, Dr. Priestley, Dr. Calvi, they got a textbook, direct displacement-based design. Highly recommend that, and I'll show you why in a couple of these case studies. It's really just a linear response spectrum analysis that it estimates. It's based on the target response spectrum. You know, if you do a nonlinear response history analysis, you got to have that target response spectrum, but then you got to have ground motions that are compatible with that DRF. For the SSM, the substitute structure method, you just need that target response spectrum. It uses a secant stiffness, the maximum displacement, so it is typically an iterative procedure. The stiffness depends on it. Typically iterative. And you use effective damping. There's lots of damping rules. So I'd say the key to successful use of SSM, you got to have two things, right? You got to have effective damping model, and you got to have a response modifier for that effective damping. You get those two things right, you can get a pretty good handle, a pretty good sanity check on detailed nonlinear response history analysis. So I did the preliminary design with the SSM, and then we did the final design with nonlinear response history, which I would say is generally speaking the way you'd want to do this. Maybe someday we'll be comfortable enough with SSM, I think nonlinear response history analysis will become more and more today's guidelines. If you're selecting ground motions, what's important? Research that says the number one factor is match the spectral shape. Other things important: magnitude, site condition, source to site distance, tectonic environment, and fault type. Now, in the new Madrid Seismic, we don't have really any strong motion recording, right? So it's going to be pretty tough to use that fifth bullet, tectonic environment, as a criteria. The thing to remember about this slide is that the research has borne out, at least the research today, is that match the spectral shape is the single most important factor. We used software for this. We used what's called fast nonlinear analysis, FNA. So if all of the inelasticity is concentrated in what's called a link type element, the FNA is really fast compared to numerical integration. And in this structure, with the isolators installed, all of the inelastic behavior is in those isolators. So that's a really good way to model an isolated structure. Also important in ground motion selection, well, you got to disaggregate the hazard, and you got to do that at multiple periods. For this particular site, it looks like the mean magnitude and distance combination was around a 7.5 at 77 kilometers. The modal, which probably has more importance than the mean. The modal is the one that's most likely to produce that ground shape. The modal for both a 1 second and a short period, 0.2 seconds, the modal was 7.7 magnitude at 80. So when I start selecting ground motions, that's sort of the range I want to look at. Now you're going to have to violate that range, and we're certainly going to have to violate the tectonic regime, right? Options for modifying ground motions, amplitude scaling, in my opinion, by far is the most attractive method. You preserve the frequency content, preserve variability in the ground motion. You can also spectrally match either in the frequency domain or the time domain. So I said match the spectral shape is the single most important factor. Well, if I claim that, you need a way to measure match the spectral shape. And here's a couple of different ways. The mean square error and this D sub R. Those are two ways to measure match the spectral shape. And you can get in the literature and find those. That's the two I know of. I've had more success selecting ground motions based on the MSE. So that's the one I would look at. For this particular bridge, I used records from all over, Chi-Chi, Darfield, New Zealand, Ochelli, Turkey, 14 records. 7 records is the minimum required at the time this was designed. It's still the minimum required in ASHTO. Now, ASCE requires at least 11 ground motion records. I just took the 7. You don't have to do the minimum. You can do more if you get to do it. So I use 14 records for this. There's a lot of research and there's no consensus on what is an acceptable scale factor. Some people would say, some research says it doesn't matter what the scale factor is. You got a close match to spectral shape. If you have to amplify that by a factor of 10, that's a good count of the ground motion. I tried to keep that around 1 and certainly no more than 4 for this project. And I did use 4 synthetic ground motions. The ground motion databases have grown astronomically in the past 15 years or so. And if you're in the business of needing ground motion records, then that's only a subset of where you can find good ground motion records that have been properly filtered and corrected. You can get them from all over. Lee mentioned the subduction zone. If you're looking for records for Portland or Seattle or Vancouver, then the NGA subduction portal is probably a good one. If you're looking for records around the new Madrid Seismic zone, you might think that NGA East would be the right place to go. You won't find this ground motion there. But probably NGA West, you're probably going to have to use a mixture of these. Selecting ground motion for the same way. So my ground motion suite, the criteria I used, I wanted the average of the suite to be no lower than 90% of the target at any single period within the range of entry. I wanted the average to be right at about 1. Now, one thing to note is that the nature of design response spectrum is different. Is it a geometric mean of 2 horizontal components? Is it a maximum direction? If you match the geometric mean of a ground motion record period to a maximum direction target response spectrum, you completely have your modification of that ground motion. It's critical to know, is it a geomean or is it a maximum direction? So at least today, as I understand it, ASCO is still using geometric. ASCE is using maximum direction for road D100. So if you're doing business in buildings and bridges, make sure you're selecting your ground motion. Match the right thing. You compare apples to apples. I'll bypass this one. I'll just briefly mention that, you typically use 5% damping. And if you're doing non-linear response history analysis, that's probably too high to use as your initial damping. Some would say just use 0 for that initial damping. But there are ways to reduce that. A summary from the substitute structure method, I got 8.02 inches of seismic demand on these isolators. From the nonlinear response history analysis, we got 7.85 inches. And for the non-isolated conditions, here's how it really was important for this project. For the non-isolated bridge, that pier attracted 8,000 kelvin. In the isolated structure, I estimated 1,185 kelvin from SSM and 857 kelvin from the non-linear response. 1,100 versus 8,000. You save a ton of money on your foundation. We're in the embayment here. We're grouting friction piles. I've had projects in the embayment where the friction piles had to be 200 feet before we got. So you can save a lot of money on piling and foundation. And yeah, those isolators are expensive, but you saved a whole lot on piles on that project. So the SSM, you got to have some way to do these higher mode effects, and that's why the pier force was higher for SSM than it was for nonlinear response history. I made conservative assumptions about the substructures and the superstructure being completely out of phase. Isolator geometry, use lead plug, lead rubber bearings on that project, and there they are installed. I'll also talk about I-40 over the Mississippi River briefly. You may have heard this one in the news the last 2 or 3 years. It's a tie girder, 900-foot spans, and one of the tie girders had a major crack in it, so it was in the news a lot. It had very expensive retrofit for that tie girder. This bridge was seismically retrofitted beginning around 2000. It was a long project, but what we did, we put friction pendulum bearings at 6 locations, 2 locations at each support. 8'10" diameter. This is a $275 million project over 13 years. 4 feet of movement in those bearings. Again, these were designed for a higher contingency range, more rare than what the design event was at that time. I used the substitute structure method on this one, so the straight middle gray line is the undeformed structure. The black line is the nonlinear response history analysis, and then the sort of other gray line is substitute structure. So I actually, using substitute structure, I overestimated the displacement at the end here. I was pretty darn close on that middle here for how much displacement to expect in those friction pendulum isolators. State Route 3 over the Wolf River, we used reduced moment capacity column bases. Why would you want to do that? We'll say I've got a 4-span bridge and that middle pier is in deep water. I might want to put a reduced moment column base there to save on foundation. So I've got these most difficult subsurface conditions. So that's the reason we use those. That's another strategy that might help when you get into performance-based design. You're having to meet criteria and multiple hazard levels, different criteria. You know, with performance-based design, you might want to stay elastic for the 100-year event just to get them. And you might want to use them. So some challenges ahead for performance-based design. This performance-based design guide has multiple hazard levels. Right now, our design response spectrum is distinct. So there's got to be a way to come up with the design response spectrum. Ground motion selection and modification I mentioned, and the long transition period piece of L. This is a slide that, for ground motion selection, you know if you've got the right answer or not for this one. So this plot really shows a lot. The top of the chart shows the minimum, the average, and the maximum of the sweep to the target. Said I want that average around across the range of periods to be about 1. It's exactly 1 year. So the period range of interest is less important. For this structure, I was interested in a period range of about 0.25 to about 3 seconds. Not really worried about what happens outside that. But I had an average ratio of the sweep to the target of 1. The smallest ratio within that period range was 0.97, and the largest was 1.06. The sort of gray line with the gold line running through it, that's the standard deviation. I had a target, I set a target standard deviation of that. And that's the average, that's the actual standard deviation. But you know, as Lee said, ground motion variability is real. You don't want to eliminate that. And that's one of the reasons I recommend amplitude scaling over spectral matching. Spectral matching, you're artificially reducing that variability. The corner period is important. You know, in the Madrid Seismic zone, that corner period is mapped. You know, it's 12 seconds. 12 seconds is probably the right number to be used if you're designing for that rare event. But with performance-based design, this lower magnitude event may be controlled by a magnitude 5. Magnitude 5 of this lower event, then that corner period, which defines the maximum possible spectral displacement. Using that 12-second value is probably grossly important. So there's some work that needs to be done on that point. Some strategies to consider, I've mentioned pipe restrainers, isolation, reduced moment column bases. Ductile superstructure, we're close there. It's really not been implemented yet. The idea of having ductile cross-frames transversely and maybe buckling restraint braces longitudinally may be a very good way to run business for seismic resilience in the future. Let me show a couple of tools. This is the ASCE 7 hazard tool. This is for building. Don't use that for business. There's also an AASHTO 2023 risk target design, and it is a beta version. I looked at those two. I looked at Shelby County, which is where Memphis is. Looked at a site class D on the left sketch, and actually those two fall pretty close together. I would have expected to see more difference. You got to think about everything going on here. You got risk targeting, you got geomean versus maximum direction. There's all sorts of things. And my final slide, I'll note that if you picked up the 22-point DRS today and compared it to the 2-point DRS for Dyer. Now, Dyer counties in northwest Tennessee, they're really close to the seismic zone. Then you would get The 22 point would be less severe at about 0.65 seconds or less. It would actually be more severe at about 0.65 seconds. So there's a lot going on with seismic design and the criteria that we use today. And I'll finish with that.